Hi everyone, let's talk about linear momentum and its conservation. We previously defined what the linear momentum of a particle is. So the linear momentum of a particle is defined to be the linear momentum of a particle is defined to be its mass times its velocity. A particle of mass m traveling with a velocity v is equal to, so that's called the linear momentum g, that's equal to m times v. Okay, and then the balance of linear momentum, or Newton's second law, Euler's first law, is F equals g dot. So the sum of the external forces acting on the system is the rate of change of the linear momentum. On a system, here the system is our particle, is the rate of change of its linear momentum. So that's just what this mathematical statement means. Now, there is another way to write the balance of linear momentum, that is its integral form. So we can integrate F equals ma or F equals g dot with respect to time. So F is equal to g dot, which is dg by dt. I can integrate this equation with respect to time between times t1 and t2, say. Okay, now this side of the equation, by the fundamental theorem of calculus, that's the linear momentum evaluated at t2 minus the linear momentum of the particle evaluated at t1. So at the end we get the integral of f dt is equal to g at t2 minus g at t1. This here is the linear impulse linear momentum equation. Okay, so this side of the equation, the right hand side, that's the linear momentum side, and that's the linear impulse side. So the linear impulse of a force is just the integral of f dt. Question: which equation is more general? Equation 1 or equation 2? Take a second, think about this. Okay. The answer is that equation 2 is more general. Because to be able to write this equation, we need to be able to differentiate this equation. So f needs to be continuous, g needs to be continuous so that its derivative is defined. So from math, the derivative of a function is defined, or a function is differentiable. Under a set of conditions. It needs to be continuous and it needs to be smooth. However, so to be able to write equation 1 or form 1 of the balance of linear momentum, the linear momentum needs to be continuous and smooth. if the linear momentum is not continuous and not smooth, we can not write equation 1, but we can still write equation 2. Okay, so 2 is more general because 1 requires that G is continuous and smooth. 2 does not. In what cases would G not be continuous or not smooth? If you have sudden changes in velocity, maybe if you have impact, for example. So there's a sudden change. If for example, I have a ball that's bouncing on a surface. When the ball is impacting the surface at this instant here, the ball has a sudden change in its velocity. Its acceleration is not well defined. The acceleration being the derivative of the velocity being a non-smooth quantity, then its acceleration is not defined. Okay. Another question. When or under what conditions is the linear momentum of a particle conserved? Momentum okay, let's think about this. You can pause the video and think about it. The linear momentum of a particle is conserved, meaning that G, which is the linear momentum, is conserved, meaning that it's constant, meaning that G at T2 or G at any time is the same. So, which means that if you look at equation 2, the right-hand side of equation 2 is 0. This means that the integral from T1 to T2 of f dt is equal to 0. So the linear impulse of all the forces is equal to 0. If you look at equation 1, if G is differentiable, if you look at equation 1, if G is differentiable, then if G is conserved, G dot is equal to 0, then this means that F is equal to 0. So if F is equal to 0, which is also equivalent to the integral of F dt is equal to 0 if F is smooth, then the linear momentum of the system is conserved. So if the sum of the external forces acting on a particle is 0, then its linear momentum is conserved. Okay, that's great. Let's think of an example. If I have a block resting on a ramp, consider a block resting on a ramp. What are the forces acting on the block? I'll isolate the system, I'll draw its free body diagram, the weight force, the normal force, and the friction force. Here I need to specify that the surface or the ramp is rough. Okay. If the static friction criterion is satisfied, the magnitude of the friction force is less than or equal to mu Sn, then the block is sticking to the surface. The fixed surface. So its acceleration is equal to 0 and its linear momentum is conserved. Constant linear momentum of the block is conserved. Okay, cool.